In section 2.6, we're going to define ionic and molecular covalent compounds. We're going to predict the type of compound formed from elements based on their location within the periodic table, and we'll determine formulas for some simple ionic compounds. So we've seen that in ordinary chemical reactions, the nucleus of each atom and thus the identity of the element remains unchanged. So electrons participate in chemical reactions, not protons. And that these different reactions are going to happen through the gain or loss of electrons to form ions. If we picture this, we have a sodium atom here. It has 11 electrons. When we remove one, it actually gets smaller. The radius decreases. We get 10 electrons, and it winds up getting this positive charge here because it's lost that negative electron. So the periodic table can help you with predicting the ionic charge that you should expect for the main group elements. Many main group elements lose enough electrons to leave them with the same number of electrons as an atom of the preceding noble gas. So group 1 loses 1 electron, it has a +1 charge. Group 2 is going to lose 2 electrons, it's going to have a +2 charge. On the other side of the periodic table, they're going to want to start to gain electrons. 17 will gain 1. Group 16 is going to gain 2. And so let's look at some examples of that. We have calcium here that's in group 2. We'll expect that it's going to lose 2 electrons and it's going to have a +2 charge. Bromine is in group 17. We're going to expect that it gains an electron and it now has a -1 charge. So moving from the far left to the far right in the periodic table, positive charges of cations are equal to the group number. Moving from the far right to the far left in the periodic table, negative charges of anions are equal to the number of groups moved to the left of the noble gases. That doesn't really work for transition metals because they actually can have multiple different charge forms. So let's picture this a little bit. It's a lot easier with it all laid out here. So basically in group 1, right, lithium wants to be like helium. So it's going to lose 1 electron so that it would have the same number of electrons as helium. Similarly, sodium wants to lose 1 so that it can be like neon. All right. Over here, though, oxygen, it wants to gain 2 electrons to be like neon. Chlorine wants to gain 1 electron to be like argon, and so on and so forth. So we get this definite pattern here to how these are going to happen. And then the transition metals are just pretty much unpredictable. We really don't know what kind of charges we're going to find on those guys. So far, the ions that we've discussed have been monoatomic ions. They only involve 1 atom. However, there are polyatomic ions. These are going to be like electrically charged little groups of atoms, and they're going to tend to never really break up. They're always going to be kind of together and moving like a little group, almost as if they were just a single atom when you're kind of arranging things. Here are some common polyatomics. This table is available here and in the book, and this is going to come up. We're going to be working with these as we go through the class, and it's important to start to recognize them when you see them inside of molecular formulas. Let's look at some stuff. There's a system for naming the oxyanions, polyatomics that contain oxygen. When a non-metal forms 2 oxyanions, 8 is the suffix used for the ion with the larger number of oxygens. Ite is the suffix used for the ion with the smaller number of oxygens. When a nonmetal forms more than 2 oxyions, prefixes are used to ate and ite. So you're going to have per, ate, ate, ite, and then hypoite. So an example of this would be like there's perchlorate, then there's a chlorate, then there's chlorite, then there's hypochlorite. All right, so covalent versus ionic bonds. So when electrons are transferred, ions form, and an ionic bond can result. These are electrostatic forces. They're pretty powerful bonds that hold the atoms together. However, when electrons are shared between the two atoms, a covalent bond results. We classify compounds according to what kind of bond they have, whether they have an ionic or a molecular bond. So, metals readily lose electrons. We saw that before when we were trying to predict the ions that we would see in the periodic table. Nonmetals readily gain electrons. When a metal and a nonmetal react, the electrons are transferred from the metal to the nonmetal. Okay, so that electron really wants to be with the nonmetal more than it ever did with the metal. So metals and nonmetals generally form ionic bonds. And so the compounds that are made from metals and nonmetals are called ionic compounds. Here's an example. We have sodium chloride. When we have one sodium atom, it gives up an electron. Chlorine readily accepts this electron, and we get the ionic compound NaCl, or normal table salt. We can do the same thing with calcium, only calcium is going to give up 2 electrons. So we're going to need 2 chlorine atoms to accept 1 electron for each one. And we get this ionic compound calcium chloride, CaCl2 in this case. So what are some properties of ionic compounds? They're typically solids. They typically have a really high melting point or a boiling point. They're not conductive when they're solids, but when you melt them down and you free up those ions, they're now able to conduct electricity. This has been used pretty extensively in industries for various different purposes. Some of the very first fuel cells were based on molten salt. Ionic compounds do not have a charge themselves. Overall, they are neutral. And what we do is we use this to determine what the ratios between them should be. So if we look at our example down here, we have aluminum with a +3, and we have oxygen with a -2. If one oxygen came over here and bound to this aluminum, it would still have a +1 charge, and it wouldn't be a neutral species, okay? Similarly, if we just took 2 oxygens and put it over here, well, then I would have +3 and a -4. It would have a negative charge. So what we need to do is find the least common multiple between these two. So what we're going to have to do is have 2 aluminums for a +6 charge here, and we're going to have 3 oxygens for a -6 charge here to ultimately yield our neutral aluminum oxide. So a lot of times, rather than individual monoatomic ions, we're going to have polyatomic ions that we're going to be working at. with. As we talked about before, the polyatomics are going to be treated as discrete units. And typically they're stuck inside of parentheses in a formula to indicate that they are a group of atoms that behave as one unit. Our example here, we have calcium phosphate. Calcium is a +2. We're going to need 3 of those in order to give us a +6. We're going to counterbalance that with 2 phosphate polyatomics to give us a -6 so that we get our neutral species. And we're going to put these parentheses around the phosphates to indicate that those are all working together as one unit. Covalent compounds. Molecular compounds or covalent compounds result when atoms are shared. They exist as discrete neutral molecules. They're usually formed by a combination of nonmetals. There often are gases or liquids that are going to boil really easily, or at least low melting point solids.